Thank you for the nice introduction. My name is Marcel Aubart, and I present today our work on a multimodal hybrid retrieval framework for digital twins in civil and structural engineering. And this is a joint work from the chair of computing at the Geodetic Institute of Aachen and from the Design Computation Institute in Aachen, and it is also part of the CARE Excellence Cluster. So let's go into the background and motivation. As most of you probably know, we are still in a phase where we need to adopt digital twins in general and integrate like monitoring data into them to simulate and enable predictive maintenance. And one of the core challenges is that we use a lot of different data sources, a lot of different formats, and even in the same domains, we have like a lot of different data formats especially. And this results in an interoperability gap where we have only partial solutions, and we also lack standardized schemas, and we have like very fragmented workflows between especially BIM and GIS and monitoring systems. So just to get to like what CARE or the CARE initiative is about, it's about climate neutral and resource efficient construction, and it's about shifting the construction industry in a more towards a more ecological space. And for this it is really important that we have like data-driven solutions to have like all the data. We can look at everything and find solutions for the future. So regarding the problem statement, as you can see, we can roughly have like two boxes of data. We have like symbolic data and subsymbolic data. Symbolic data is well structured, like for example IFC models or vector geospatial data. And on the other hand, we have like subsymbolic data like sensor streams, point clouds, images, orthophotos that are hard to get and less structured. And so we are in need of developing methods to get them together and link those data. And here we get to our study scope. So we want to build a prototype that is hybrid symbolic and subsymbolic from the architecture. And we use, in our case, PDF documents to build like a retrieval layer and have like multimodal data in that case, since PDFs include like images, tables, and text. And the key concepts that we are talking about here are retrieval-augmented generation, and our approach is a hybrid RAG that combines both, like a vector RAG for fuzzy similarity search for the subsymbolic data and the graph RAG for like the symbolic data that is more like structured. And we came up with three research questions. The first one being if a hybrid knowledge graph plus vector system can outperform the single paradigm approach. The second being, does ontology alignment improve the retrieval accuracy? But this is more like for the whole project. And lastly, our hypothesis is that a hybrid knowledge graph plus vector database architecture enables like better retrieval accuracy. So here you can see on the right side our whole project, our whole concept that we want, starting from data spaces on the left side that should be sovereign. They should be domain specific, and we want to align them with different ontologies and encoders. Then you can see on the right side what this paper is mostly about, that we try to build a system on a knowledge graph and a vector database that work together to retrieve better data, and we have like the design principles to be fair and to be data sovereign and make it as modular as it can be, so that we can extend it in the future. So for the technical infrastructure, I will just quickly go through this one. For document ingestion, we can automatically ingest PDF data. For the images, we use like Grand3 as a visual language model, and we auto embed and index them. And for our retrieval layer, we use Quadrant as a vector database for like the vector similarity search, and Neo4j as our graph database for the semantic graph. And in the generation layer, we then use Olama Mistral to interact with like our whole system and be able to get like user inputs out of it. So let's get into the results of our test. We used the Open RAG Bench dataset, which includes 1,000 PDF documents that include all kinds of data, like images, we have the tables, and it has like 3,000 queries where with gold answers what you want to expect. and we embedded all of those tables, and then we tested our 3 approaches, like the 2 single paradigm approaches, the vector rec and the graph rec, and then we compared it to like the combined approach with the vector rec. And you can see that the vector rec improves in every category. It improves on query hits, like correctly retrieving the right document in the query with like 18.83 hits on average. And then we have like the mean reciprocal rank, which is like the ranking quality if like the best document is on top of our search. Here it also excels compared to like the other models. And then lastly, the average retrieved documents to get to the right answers also on the same state as like the vector rec. So in total, we can say that the results support our hypothesis. And as an outlook, our key findings are that the hybrid rec outperforms both the single paradigm approaches, and that we sadly didn't came to like the ontology-driven alignment at that point, since we used like Neo4j, and this is like a property graph underneath it. We didn't even use ontologies by definition, and we also can say that our hypothesis is true, that the hybrid knowledge graph plus vector database excels at heterogeneous data in our case. And the core contributions is that we interlinked like those 3 sorts of data. And for the future work, as you saw before, we had like the huge graphic on what we want to do. And we have like the 3 points, like the 3D viewer and dashboard, which is 3JS based, and should also include geospatial features at some point. And we have the multimodal extension. Since we are in construction engineering, we want to include also IFC models into it, point clouds, sensor streams, construction plans, and we want to be able to query through all of those data. Then we want to do a transferability study, since when we only validate it on one case, it doesn't make sense. We want to have a system that works on many cases. And for this, we will also do like use case validations, and here we plan to do one on lifecycle assessment and the benefit of this system on it, and also on structural monitoring. And since our project started in January of this year, we didn't have that much time for the paper, so I want to give a larger outlook and a look into our current work. And here you can see on the right side our current viewer implementation. And here we are able to load IFC models from our database, point clouds from our database. We already included the retrieval chat. We included functions for cutting into sections, cutting through the point cloud through the IFC. Also, there are overlays for sensor data and for measurements of the IFC. And why does this matter? We want to have like one system that is web hosted that an engineer can access and say, okay, I have all the data, I can query through them with natural language and see everything in an instant. And then I also want to go into multimodal extension. We, at the moment, already included IFC data into it. We included point clouds into it. And here you can see our knowledge graph, and why is the knowledge graph important? Here's another example. For example, when you have your IFC loaded and you click on one part of it, you probably want to know, okay, what information are there for this part of the IFC? And you can see on the right side that all the chunks that are retrieved, in this case from construction plans, that belong to the IFC. And we can also go in the other direction, ask the LLM about, okay, what can you tell me about pillar 10 in this case? And it will point to the IFC, will highlight it, and tell you all the documents it can find about like a specific question. And lastly, we are currently working on integrating and automatically fitting point clouds to the IFC model to enable automatic as build and as design comparison down the line. And that's it from my side. Thank you for your attention.